Now keep in mind, most of what we're going to talk about in these slides is done automatically for you in the IDE and the motor setup. But it's nice to know what some of these underlying features are that we're working with. So basically, to power PMAC is a set of algorithms that execute repeatedly to do the function of creating a motor in power PMAC. So to power PMAC, a motor is a software, entity. And basically a motor uses a number of these algorithms. There's trajectory generation that would come from some kind of like a motion program that's generating a trajectory or generating a motion sequence for the motor, or there could be jog commands being issued by a host computer or from a PLC. There's servo loop closure using feedback and feed forward. The phasing algorithms, commutation and the current loop closure. Housekeeping, which is fault detection for the motor. Status and status update for the motor. So there's a set of memory registers organized in a data structure. The saved setup data structure elements. There's unsaved control elements for the motor. And then there's status elements for the motor. For example, fatal following hour for motor is a status of the motor. There's linkages to input and output registers to connect the motor to the real world, defined by addressing saved up elements. Remember, we talked about the elements that would have the lowercase p in them, in their element name, indicating that they're a pointer to something. So that's how we take the software creature called a motor and connect it up to all of the real hardware. All of the stuff that we just talked about, these ASIC registers, are all done by these pointers. And then the real I/O registers that tie to the physical actuator and the sensors, the feedback devices. Or they could be network registers communicating over a network like macro or EtherCAT. Or you can use memory registers for a pure software or virtual motor, where there is no actual output, there is no actual hardware feedback device. It's just a motor internally running as a software structure or as a software entity inside of Power PMAC. Motor number start at 0. The maximum motors is set by sys.max motors. The default is set to 32. You could, the highest you can set that to currently in firmware is 256. So current Power PMAC firmware is capable of controlling 256 motors. We do that at default of 32 so that when you do a backup, when you type save, and then Power PMAC saves all of the saved structure elements in ppsave.cfg, be a lot of code for 256 motors, especially if there are hundreds of elements for each motor, closing in maybe on thousands. So we're talking close to hundreds of thousands of entries in a configuration file. Auto assignment of servo I/O to hardware gates that we're connected to always starts with motor 1. So when you do a $triple triple star, Power PMAC goes out, looks and see what all the hardware you're connected to, and automatically assigns all of the elements for motor 1 to that first channel on the first gate, and motor 2 to the second channel on the first gate, and so on and so forth. So a lot of Power PMAC setup is already done for you by the firmware by virtue of the auto assignment of servo I/O. So they will not use motor 0 for control of a physical motor, and most users wouldn't want to use motor 0 for physical control of you might want to save it for custom pre-processing of servo data or a virtual motor to be used as maybe master position for your application. So #X is how you specify a motor in PMAC, if we just pop over here to the executive, and we look and we ask Power PMAC, what is the current motor I'm addressing? I'm currently addressing motor 0. By default, on I power cycled my PMAC, so I'm addressing motor 0. I can give the addressing command #1 to address motor 1. And now if I ask Power PMAC what motor is it addressing, it remembers it's addressing motor 1. If my motor was now activated and tuned, which it should be, I should have a perfectly tuned, perfectly activated motor. I could give it a jog command, J-. Okay, so apparently on this one I'm not activated. I was misguided by one of my setup guys, told me I had a completely activated box, but we'll go back and check it shortly. I believe everybody else's should have a standard configuration loaded into the box. So the X data structure element refers back to the motor sub X dot element name. And for those of you that are familiar with Turbo PMAC, there's legacy I variable support for existing functions on motors 0 through 31. So considering that Turbo PMAC had I variables I0 through I99, that would actually, in Power PMAC wouldn't consider that as the old global I variables for Turbo PMAC. Power PMAC is going to look at that as the standard I variables for motor 0. So when we say legacy I variable support, if you're a previous Turbo PMAC user and you want to know what's the structure name for IXX16. So I go I116 for motor 1. I give it the definition symbol, and it will come back and it'll tell me, oh, that's the motor 1 PWM scale factor. So if you're trying to think of what is the power, for those of you who are familiar with Turbo PMAC, so if you're trying to think of what is the structure element for this Turbo PMAC I variable that I remember, you can type in this, use the definition symbol, minus sign greater than, and you know what, let me make these characters bigger. So if you can think of an I, but you can't type any of the generics, so you can't say I7MN0, you have to say I7210. You can't say IXX66. You have to pick a motor number and say I166 or I266. So one of the nice features of the IDE is the motor setup tool. And we'll be going through this in quite good detail tomorrow. But I'm going to give you a couple of little pre-advanced screenings here of what we get in Motor IDE setup. So if we go to the Tools menu, we can select System Setup, and we saw the screen before. We can select a motor number. We can tell it to add a motor or give it a motor number. We can see down in the output section it tells me I've just added a motor to the setup. In this output section there are, in this section at the bottom there are 4 tabs. So there's the actual output that was sent to PMAC. There are some debug messages, there's setup messages. So as I'm going through this motor setup, I can tell it the amplifier information. In fact, what amplifier do I have? I have an amp 2. And notice in the drop-down box, once I've selected Delta Tau as the manufacturer, I can select any number of the amplifiers that we can provide. Mine happens to be the AMP2. And then it will populate all of the entries in here, only a few of which I'm allowed to change. And basically, by a process of going through each step of the motor setup, the IDE motor setup utility tool will automatically set up your motor for you. You tell it what kind of amplifier you have. If it's in the drop-down list, you can add your own information to each of the databases. So you can add your own amplifier information, you can add your own motor information and feedback product information. And then it goes through basically a wizard-style setup that will then set up the motor, verify the feedback is working properly, test the output of the amplifier, tune the motor somewhat reasonably well. Usually, it's expected for you to go back and use the tuning tool to get better tuning on your motor. But we're going to go through this in great detail tomorrow when we go through motor setup. In fact, we're going to do a couple things. We're going to set up a simple motor by hand by entering all of these structure elements that I'm going to hopefully finish up in the next couple of hours. And then we're going to use the setup tool to do it for us automatically. We already talked about the setup variable screen, so you can actually go in and access all of the motor setup structure elements through that screen. Let's talk about some of the basic structure elements. So motor sub x.servo control. This specifies whether the servo is turned on or not. If it's 0, the motor's not even turned on, so there's no servo tasks being done. If it's set to 1, the servo is activated in standard mode. So it's our standard trajectory mode with servo loop tasks being done. There's another setting, 8, and this puts it in Gantry follower mode. So it's not looking at any of the output of trajectory generation. It's only going to look at whatever motor that it has been linked up with as the Gantry leader motor. We'll talk about that a little bit later when we get into these Gantry, some of the special servo features that Power PMAC has. Motor sub x.phase control. This sets up whether the phase task for the motor is turned on. If it's 0, there's no phase task. If it's set to 1, then commutation is done with packed values from the ASIC. If it's set to 4, it's done with unpacked values from the ASIC. This is more typical with the PMAC 2 style AC or macro IC. With the PMAC 3 gate, depending on what amplifier you're connected and what other features you may want from the amplifier, you may or may not do packed or unpacked. Motor sub X P80C specifies whether or not current loop has been enabled and what is the address. So if it's greater than 0, it enables the current loop feature for that motor, and it also sets what the feedback address is. So you're going to be pointing to one of the ADCs. So if we take a look at how Power PMAC is controlling all the way from trajectory generation through the position, the velocity filter, through phase commutation, through the current filters for doing current loop, all the way out to the power block. This is what defines these different modes of motor amplifier operation. So if you're just in pure position mode, which Power PMAC can do, it's taking the output from the trajectory and just sending it out as a pure position value. This would be commonly used in something like EtherCAT, where EtherCAT, you have an EtherCAT drive that is a pure position mode drive only. So you're just sending a position command. Power PMAC doesn't care about the feedback. Power PMAC doesn't care about the following error. Now, having said that, if you do use a pure position mode amplifier over EtherCAT, you lose a lot of the amazing internal features that Power PMAC has. Going from there, we have velocity mode, torque mode, sine wave mode, and then direct PWM drive mode. These are all of the modes that Power PMAC can support. So, position output command. There's really no feedback loop closed in Power PMAC. Just the numeric output is sent out from Power PMAC, usually to a network drive. This is also a technique by which you can create a virtual motor. I might talk about that a little bit later on, or we might show that when we get into some motor setup. Velocity output command. So position loop is closed in Power PMAC, but the actual output from the PID loop is a velocity command, not a torque command. This is typical in the pulse and direction setup, where you're sending out pulses at a certain frequency, so that's considered a velocity command. Torque command output. This is the one that's most commonly used and probably gives you the best controlling technique with Power PMAC. So the output now is a torque mode or a torque value to the drive. You're sending a torque value to the drive. In plus or minus 10 volts, which can be velocity or torque mode, you have better control if you're in torque mode than if you're just doing velocity mode. And that's almost always determined by the type of drive. So on a typical velocity mode drive, there has to be a feedback device going to the drive so it knows what speed the motor is going at, so it knows how to take care of its own internal current loop. Then there's the sine wave phase currents command. So this is where position and velocity loops are closed. The commutation is done in Power PMAC, but the drive is taking care of the current loop inside of the drive. So normally what you would have in this mode is you would have two analog outputs from Power PMAC going to the drive. And then the best of control is direct PWM. So Power PMAC is not only outputting the three phases going to the motor, but it's also controlling the current loop. And basically, the drive is nothing more, and let's just back up here real quick. The drive is really nothing more than just a power block. Power PMAC is doing all the rest of the control inside of the motion controller. And one of the nice features about having that kind of setup is the more that you have in the drive, the more that you have to set up in the drive itself outside of Power PMAC. It might not be a simple thing. You may have to connect up with external software to the drive, or you may have to tweak pots on the drive, or you may have to use interchangeable modules on the drive to get those features set up on the drive. If direct PWM with current loop control is done at Power PMAC, now everything is set up as registers in Power PMAC. So let's take a look at some of the motor addressing elements. Remember again that the element starts with a P. It's a pointer to something, so it's looking for an address value. You want to set it to an address value. Like motor sub x dot p limits. This is looking what address is it looking for its limit switches. And the value is always given as a register element name dot a. It is possible to give it a direct address value if you wanted to, but normally there's no need to do that because there is a structure element name for the address that it should take on. So in this case, we could use gate 1, index 4, channel 0, status.a. So the A means the address of. So some of the servo function addressing elements, motor sub x.pdac, this is the output of the PID loop. PANC and PANC2, these are the feedback. So you could have a single feedback or a dual feedback. There's also a pointer to a master encoder. So if it's going to be a slave to another master output, P master enc. Elements for the flags. So there's motor sub x.p limits, P amp enable. Where's the amp enable flag coming from? P amp fault, P cap flag. Where are the capture flags coming from? P cap pause, P enc status. What kind of encoder is it pointing to? P enc control, P enc loss. So we'll talk a little bit more about these in detail in a few more slides. Phase function addressing elements. So there's motor sub x dot phase enc, P phase enc, PADC, P sign table, P volt sign table for some of the features that you would need in commutation. If you have power on, absolute power on elements, so you have P abs pause for your power on absolute position and P abs phase position, P ab phase pause for the absolute power on phase position. The default settings of all of these, when you do a triple dollar, triple star, are made based on the actual hardware that Power PMAC can see during the triple dollar, triple star sequence. So again, a number of these get set up automatically to the correct value, the value that you will need for the type of control that you're doing. Power PMAC is going to go out and it's going to see I'm connected to an accessory 24E3 that has the first two channels of analog outputs and the second two channels is direct PWM. So it's going to correctly set for channels 1 and 2 everything I would need for analog control and channels 3 and 4 for direct PWM control. So max motor sub x.pdac, this is the command output address. It's going to look at the first PWM register or the first DAC register or the first PFM register. There's only one PFM register, the one at the very end, the D phase. If I have a macro setup, if I have a macro IC in there, it's going to point some of these to the macro IC. Do I have a macro IC on this one? No. If I had a macro IC on here, that would be, depending on whether it's a gate 2 or a gate 3 macro IC, it's going to set up at the end, after it sets up automatically for my first 4 motors, it's going to set up all of these macro registers for all of my different pointers for the inputs and the outputs of my Power PMAC. So motor sub x.penc and penc2, the penc is for the outer position loop feedback address and penc2 is for the inner loop feedback address. Always these are going to point to an encoder conversion table entry. By default, Power PMAC is going to set them both to the same encoder conversion table entry. And I think we're going to see that in just a few seconds here. So if we have a dual feedback motor, we have 2 encoders. There's an encoder on the load and an encoder on the motor. So penc1, penc is going to look at the encoder on the load, and penc2 is going to look at the encoder on the motor. So typically, if this was a commutated motor, PMAC is going to do all of its commutation off of the encoder on the back of the motor, but it's going to do all of its position control off of the encoder that's on the load. Motor input flag addressing element. So we have penc status. This is the parent input flag address. So this is used by Power PMAC to set up the other input flag variables when the motor encoder type is set. So if it knows what type of if it has the encoder type, and we'll show that in a couple of more slides, the exact details of what's going on there. So if the other input flag address variables are equal to that, then it doesn't have to reread the register. So motor P cap flag, this is the capture trigger flag address. So typically, if we have, for example, a gate 3 ASIC, if we know that we're looking at channel 1 of that gate 3 ASIC, then we're going to be looking at channel 1 for the capture flag, and we know what bit the capture flag is at. We're going to look at channel 1 for the limits, and we know what bits the limits are at. We're going to be looking at channel 1 for the amplifier fault, and we know what bit the amplifier fault is at. Notice how in Power PMAC now, different than our previous set of motion controllers, we have the address of where it's going to go look for its flag feature, and then what bit it's located at. So this gives us a much easier way to, for example, I could just generically go out to any I/O card, and I could say, oh, I'm going to bring in my over travel limits off of this I/O card. I'm going to bring in my amplifier fault off of this I/O card. I'm going to send out my amplifier enable to this other generic address, and you can do that. Of course, it's important that the capture information come from our capture hardware if you want to use our built-in capture features. But if not, you can use software capture. We do have software capture ability in Power PMAC. So some of the common values used are the channel number status register for these pointers. It's important to get the bit number right. If you use the standard channel status register, then you got to make sure you get the bit numbers right. But again, the firmware is going to automatically set those up for you. So if I was to go look at one of those on oops. Let's see. One. Oops. I think I need to spread this out a little bit. PCAP flag. So we can see that it's looking at the first channel of my accessory 24E3. Notice it's using the alias name. It will always report the alias name. I can type in gate 3. I can type in gate 3 sub0 dot channel 0 dot status A, but it will always report back the alias name. So notice it reported back the alias name. We could also ask for its bits. Oops, need to get the dot in there to start the IntelliSense. That's how IntelliSense, by the way, knows to start re-looking in its databases as soon as it sees the next dot in the sequence of the structure access. So PCAP, so cap flag bit, and it has automatically set it to the right bit for a gate 3. Output flag addressing elements. Again, we tell it the parent output flag address. And it's used to set the other structure names when the encoder type has been properly set. So PAMP enable is the flag address for the amplifier enable and amp enable bit. So it will automatically get set depending on which type of gate that we're using. So motor encoder type, this specifies the feedback and ASIC type used. So if it's set to 1, it's a quadrature encoder with no extension on a PMAC 2 IC. If it's set to 2, it's a quadrature encoder with 1/T extension on a PMAC 2 IC. If it's set to 3, it's a sinusoidal encoder on a PMAC 2 IC. If it's set to 4, it's a macro ring feedback type. If it's set to 5, it's a quadrature encoder with 1/T extension on a PMAC 3 IC, which is the default for almost all PMAC 3 gate products. 6 would be a sinusoidal encoder on a PMAC 3 IC, and 7 would be the extended sine arctangent interpolation for a resolver on PMAC 3. So again, these are automatically set on a triple star reinitialization because the power PMAC is going to go out and see I'm connected to a gate 2 or a gate 3. And it's always going to assume it's using the default feedback style, which is a quadrature encoder, and it's always going to set it up to do whatever type of 1/T that gate supports. So in the gate 2, it's going to be the software 1/T in the encoder conversion table. In the gate 3, it's going to be the hardware 1/T that's done inside of the ASIC. There's a few motor scale factor elements. So this provides pre-multiplication of the feedback and the master data, but of course not the commanded trajectory, because you want that to stay, you don't want that to be interfered with, otherwise your path through space gets messed up. These work a bit differently than they do in a turbo PMAC, because now with Power PMAC, Power PMAC's floating point math, so there's a little bit more flexibility in how you would use these. So there's the motor sub x dot position scale factor. This scales the outer loop in motor units per source unit. So a value of 1 makes it the output as the output of the encoder conversion table. So you could typically use this to make your motor units scaled in the value of your actual user units. So in kinematics, this can have a great benefit because now your motor joints are in user units. It acts as a gain term because it is multiplying the feedback value coming right out of the servo loop. So you'd have to change the servo.kp, which is the proportional gain for that motor, to compensate for that. And consider also, since you've changed the concept of what a motor unit is from an encoder unit, now it also affects the jog speed. Fatal following error limits, because normally these are usually written in the encoder, the motor units, which are considered usually to be encoder counts. What most people will do is they'll leave their motor position scale factors at the value of 1, and then they'll use axis definition statements to get their user units in motion programs. Now, if somebody wants to be able to have their jog commands, jog speeds and things like this, in user units, then of course the motor position scale factor to pre-scale the actual motor units in user units, the engineering units of your system. Now, when you go J equals 10, you're going at 10 user units per time unit per millisecond instead of motor count units, which is what the default would be with the motor position scale factor at a value of 1.
And that can be a floating point, right?
And they're all floating points. Everything in Power PMAC, well, I shouldn't say every structure name, but everything internally is done in floating point. All of these structures are in floating point. The output of the encoder conversion table is a floating point value. One of the final entries in the encoder conversion table, and I'm going to talk about that probably in the next 45 minutes, is a scale factor that turns it into a floating point value. So from that point on, everything is floating point in the PID loop. Which has a number of nice benefits and enhancements from Turbo PMAC, where, for example, when you're doing master position and you have the IX08 and the IX07, there's only, since those are integers, there's only certain scale factors you can get from master position to slave position, but now with Power PMAC, it's all done in floating point, so you can get exactly the scale factor that you want. Motor sub X stop pause to SF, that's the inner loop, the velocity loop scale factor. Same rules apply there. So if we take a look at the basic concept of what's going on with these scale factors in the Power PMAC PID, we can see them here graphically in this slide. This is kind of a keeper slide in as much as it shows you the behavior and the action that all of these motor scale factor elements that we're talking about. So you can immediately see so there's the scale factor coming out of the encoder conversion table. There's the motor scale factor. So one of the important strategies for relating the action of two motor axes together works by directly tying the desired trajectories of the axes together. So in PMAC, you can put the axes in the same coordinate system and command them on the same program line. In other words, motor 1 is an x-axis, motor 2 is a y-axis. And if I want them to move together as a simultaneously interpolated motion, I would command motor X and motor Y on the same command line. I would give the in the motion program. And so that would give me a coordination of multi-axes. I could have two motors do exactly the same thing in the coordinate system. I could take a motor X, I could take a motor Y, or a motor 1 or a motor 2. I could define them both as a motor X. And when I do a command for motor X in the coordinate system, now both motors are going to move exactly the same way at the same time. In both of those circumstances, the only thing that is going to cause issue is if the feedback on all those axes doesn't stay tight enough. In other words, the tuning is such that there's a little bit more following error on one motor than the other. Well, in the real world output, I'll lose a little bit of my coordination. So another method I can use to coordinate motors together is I can use master-slave strategy. So in PMAC, I could use position following, electronic gearing. That's the basic technique where one motor is following another motor's, either another motor's trajectory or another motor's actual encoder value. I can also do what's called external time-based electronic camming. That gives me some more advanced capabilities, and it gives me the ability to take care of some smoothing, because in time-based, I have a few more features to give me a little bit more control over the master position value going to the slave position value. To give you a quick example of what I'm talking about, if one motor is looking at another motor's actual position and the master motor has a bit of vibration on it, that vibration is going to be immediately sent down to the slave motor. So poor tuning on the master motor will result in poor behavior on the slave motor. So now, with the external time base, the quality of the master axis feedback doesn't affect the quality of that coordination relationship. Depending on when you use it, when you use the master-slave or the external time-based electronic camming for doing this coordination, really depends on how well your feedback is compared to how difficult it's going to be to set up this kind of system compared to using master slaving compared to external time base. So basic position following functionality, electronic gearing, this is the sort of the mechanical analogy, the radius of the two pulleys, and then the amount of angular motion provided from one motor to the other. And then there's the master position scale factor. It basically is the ratio of those two radii. So in setting up Power PMAC for master position following, they're point to the master encoder, a P master enc, and then master control, whether it's enabled or disabled, and what mode that it's enabled in. We have what's called normal mode or offset mode. Basically, the difference between normal mode and offset mode is, in one case, the origin is considered fixed, and as the motor moves, the origin stays there. In offset mode, the origin is moving with the slave motor. So the slave motor always thinks that the origin is right where it was before. So if it moves 20 counts out this way and it moves 20 counts back, it's back to what it's considered the origin. That is the mode that's most typically used when you're doing some kind of activity on a traveling, let's say a traveling belt. And then there's the master position scale factor, which again is a floating point. And so it's held in a 64-bit floating point value. It's not the ratio of two integers as it was in Turbo PMAC. So this gives you a much finer way. You can get the exact gear ratio that you want between master and slave. Some of the position following enhancements we have in Power PMAC now are, there's a master position slew rate, so it specifies the rate of change of the ratio. There's also a master max speed that limits the maximum speed from following on the motor. And then there's a master max accel, which limits the acceleration and deceleration from following on the motor. Here's a few plots showing some of those advanced or enhanced features in action. Now I'm going to gloss over a lot of this material so that we can get through the basic concepts of all of the motor setup variables. Later on in class, if anybody wants to go back and ask for more detail on any of these features, we can definitely do that. Motor automatic safety check. So every Power PMAC motor has following error limits, hardware over travel limits, software over travel position limits. There's an amplifier fault input signal, I2T integrated current limit, encoder loss check, auxiliary fault check. So you can bring in an auxiliary sensor. It could be for whatever fault feature that you want to give it. There's also automatic brake controls to engage and disengage a brake on every motor channel. Commanded velocity limit, commanded acceleration and deceleration limits, and commanded jerk limits, the S-curve part of your motor acceleration and deceleration. So for following error limits, there's motor sub X dot fatal FE limit. This is in the magnitude of motor units, so whatever you have your motor unit set up to, depending on your motor scale factor and your encoder conversion table scale factor. The motor is killed. If this happens, the motor is killed immediately. Other motors in the coordinate system may be killed or aborted as set by the motor sub X fault mode. We'll talk about that a little bit later. There's motor sub X warn FE limit, and this sets the motor sub X FE warn status bit. It can also be used as a trigger an error trigger for triggered moves if motor sub X dot capture mode is set to 2. So in other words, instead of having a home switch for homing, I could just move the motor into a hard stop, and when the warning following error limit reaches a certain value, that would be considered my home position for people that have an inexpensive but simple homing mechanism. Hardware over travel limits. So there's motor sub X dot P limits, we talked about that, and then the limit bits. If it's a PMAC 2 IC, limit bits start at 25. If it's a PMAC 3 IC, limit bits start at 9, because they're at a fixed location inside the register at a particular address. Again, Power PMAC's automatic setup of these values will have the correct value in there based upon Power PMAC reading what type of hardware it's connected to. For limits, the bits must read as 0 to be considered not in the limit. This is a requirement for safety purposes. So if motor fault mode bit 2 is set to 0, there's a closed loop stop or abort. If motor sub X fault mode bit 2 is set to 1, then it's an open loop stop or a kill. It kills the motor. There's also software over travel position limits that PMAC has. Motor sub X dot max pause is the positive software over travel position limit, and motor sub X dot min pause sets the negative end travel limit. These are both in motor units, and they're always referenced to the motor 0 position. They are not affected by any of the axis programming offsets in the motion program. And both are enabled if and only if max pause is greater than min pause. So checks are made at move calculation time and move execution time. So it can actually stop on or before the limit. Some of the motor dynamic limits. Motor sub X dot max speed. This is the maximum speed for the motor in motor units per millisecond. So for most typical applications, it's going to be in counts per millisecond. It's the commanded speed for rapid moves if the motor sub X dot rapid speed select is 0. It's the maximum speed in linear moves, and it will extend the move time when it's violated. And it's the maximum speed for segments in segmented moves in linear, circle, or PVT moves if look ahead is enabled. So if we're not in segmentation, if we're not doing segmented moves, and we'll talk about this a little bit later when we get into coordinate systems, but there's two ways that PMAC can look at its move trajectory from the coordinate system, one called segmentation, one not segmented. So if you're in segmentation and special look ahead is turned on, it's going to pay attention to this motor max speed. If your segmentation is turned off, then it's going to pay attention to that without look ahead. Motor sub X in AMAX, inverse AMAX. This is in milliseconds per motor unit. Notice it's the inverse acceleration maximum. This is better for Power PMAC to do the calculation very quickly. So this is the maximum permitted motor acceleration for unsegmented moves. And it will extend the acceleration time if it's violated. So basically, if it's violated, it slows the move down or extends the acceleration time, or it slows the rate of acceleration or deceleration. And then if special look ahead is turned on and we're in segmented move, then linear, circle, and PVT moves will pay attention to this. Inverse Dmax. This is the final acceleration that you can have in a linear move. So this is an enhancement from the previous versions of PMAC. You have both a front end and a back end acceleration value that you can give, not just a single acceleration value that's used both at the front and the back, so that you don't have to break your moves up to get different decels than accels. In Turbo PMAC, you would have to have taken a single linear move, break it up, and have change the acceleration at the second part of the move to get a different accel and decel for a single piece of a move. And then there's inverse Jmax. This would be the S-curve part on a program move. This would be the maximum S-curve on a program move. So it would extend the TS if it's violated. Now, times are extended for all the motors in the coordinate system so that the path through space remains the same. So basically, your worst behaving motor is going to slow everybody down or decelerate everybody down accordingly. Power PMAC is I squared T, so integrated current limiting. So there's a couple of structure elements here. I2 T set, this is the continuous current limit. So this would be what your continuous current is that will be then will be integrated over time to make sure that it doesn't violate the I2T trip. This is this would be the integrated current limit above I2T set. And this trip would be treated as an amplifier fault. So the same results would happen based on the motor sub X dot fault mode. Is it going to fault other motors in the coordinate system? Is it just going to fault that motor? Or is it going to fault all motors on the PMAC? Now there's an important distinction here. If you're set up in direct PWM mode where PMAC is doing the current loop control, then the values used in integrated current limiting, I squared T, are the actual values read from the current sensors. If you're not doing direct PWM mode with current feedback, then it's the commanded current that's used. Encoder loss detection. This is another feature that Power PMAC has. So the loss of the feedback sensor will almost assuredly lead to a runaway condition, or could lead to a runaway condition. In many cases, it will. There's other safety checks like following error, amplifier fault that might not catch it in time. So you would want to know if there was a complete loss of the feedback. And so we can check directly on almost all of the Power PMAC Axis accessories that have an encoder input have the ability to check for encoder loss. So the setup elements for this are motor sub X P-enc loss. This is the input flag address. If you want to disable the function, set it to 0. Motor sub X enc loss bit, this is the bit of the flag at that register. And then whether a 0 is considered a loss or a 1 high is considered a loss. And then there's another setting, enc loss limit, that will allow you to select an accumulated error count before it trips. So the accumulated error count increments each scan, the error is found, and then it counts down to 0, decrements each scan of the error until that's found, and it trips when it is greater than the encoder loss limit. So it basically is so that if you have some intermittent thing going on that comes back and it's recoverable, there may not be the need to immediately kill the motor on that apparent or what appeared to be a loss. And then, of course, motor sub X dot fault mode determines what happens to other motors in the coordinate system along with this motor being killed. So typically on the 24E2 series, the PMAC 2 style gate, we have circuits in there that look at both sides of the encoder to determine that they're always in the opposite state. On the 24E3, these are internal circuits inside of the gate, so it's not external circuits that are being used. So there can be PMAC 2 style accessories some very old accessories that don't have the encoder loss. Pretty much all of the PMAC 2 style accessories that I can think of off the top of my head have the ability to do encoder loss. It does require that you have a differential quadrature inputs though. You have to have the differential inputs in order to utilize this, so it can't be done off of single-ended. We can also do by using the sum of squares in the accessory 24E3 to determine whether or not we've lost a sinusoidal encoder. And then we have the auxiliary fault detection so that you can bring in any other fault of your own choosing, maybe a thermal sensor or secondary encoder loss. And so basically there's a pointer to the fault, and then we specify what bit it is and whether low is a fault or high is a fault. And again, it has its own accumulated error count before the trip, works in the same way as the other fault. So an example of some common settings for this. If it's the thermal input on a power brick, then it's going to be set to the power brick's thermal input. If it's encoder loss on a generic gate 3 accessory, it's just set to the status of that status of that register. And then, of course, 0 will disable it. And again, the motor sub X dot fault mode will determine what happens to other motors, either in the coordinate system or on the entire PMAC. Brake control. So again, there's a pointer to the brake output that will control the brake of the motor. And then there's a bit that you specify. So you specify the address and the bit. There are two other settings, brake off delay and brake on delay, that specifies the delay in time in milliseconds for disengaging the brake and engaging the brake. After engaging the brake. So how long we're going to wait to disable the motor after engaging the brake. And there's some special online commands that utilize this. So there's a kill command and a dekill. So dekill will a disable command and the de-disable. And then we can use these commands also inside of programs with the dekill and the de-disable, the de-disable command. Emergency kills like an amp fault or a fatal falling error, of course, those will, or the standard kill command will disable the motor and engage the brake simultaneously. So automatic abort faults resulting in actions. Some of the things that can cause an automatic abort fault, so software over travel limit is exceeded in closed loop. Hardware or software over travel limit detected in open loop mode. Hardware over travel limit detected in closed loop mode. And so depending on the fault mode bit, the offending motor is going to be aborted, a controlled deceleration to a closed loop stop, and then other motors in the coordinate system are also aborted. Motion program in the coordinate system is aborted. And when you abort a motion program, and we'll get into some of those details of these features in motion programs, but you won't be able to resume at that point because when you abort a motor, it doesn't come to a controlled stop. It decelerates at a particular rate for that motor. Conditions that will cause an automatic kill for a fault on a motor. So fatal following error limit is exceeded, amplifier fault input detected, I squared T, current limit is detected, and encoder loss is detected. In these cases, you want to kill the motor. don't want the motor to continue moving at all because there's possible chance of something being destroyed. And so depending on the setting of the fault mode, software or hardware overtravel limit detected in open loop mode and hardware overtravel limit detected in closed loop mode. And in these cases, the motor is killed. So it's put open loop, zero commanded output, amplifier is disabled, and there's no delay in the engagement of the brake because this is a kill situation. So we're trying to be as safe as possible. So other motors in the coordinate system are aborted if the motor sub x dot fault mode bit 0 is equal to 0. Other motors in the coordinate system are killed if that bit is equal to 1. So depending on the setting of that, it determines what happens to the other motors in the coordinate system. And of course, the motion program is aborted since the motor was killed. And you almost definitely can't resume from that point because you don't know where you are since the motor coasted, or in some cases may have coasted to a stop. Motor jogging move control commands. So we have things like motor sub x jog speed, that's the jog speed of the motor. Motor sub x jog TA, that's the acceleration time for the motor. Jog TS is the S-curve acceleration for the motor. So for moving a motor, there's acceleration. We're at constant speed. It decelerates to a stop. That's the TA. It's also possible to have some S-curve on the motor. And that's what the TS is for. So total acceleration time, if the values that we use in TA and TS so this would be TA, this would be TS. So if TA is greater than TS, the total acceleration time is jog TA plus TS. It's just the sum of all the acceleration times put together. Once TS becomes greater than TA, TA doesn't matter anymore. Now the acceleration time is just 2 times the TS value. So once it becomes greater, that's not a good looking S-curve. So if I have TS, it's twice that for the acceleration time. Some of the motor jogging commands. So an online motor jogging command, #1J plus, or a buffered inside of a motion programmer or PLC. We could say jog +1, jog +2. And these operate on the modally addressed motors or listed motors, so we can provide a list. In other words, we could say jog +1, 2, 3. And these are indefinite commands. So if software position limits are active, it would jog into the position limit and stop. J/ or jog/ / is the jog stop command. Also, if the motor is in open loop, it'll immediately put the motor in closed loop. If the motor is in open loop and for whatever reason it's spinning, it will decelerate the motor so that it can be at the correct jog speed, whatever the commanded jog speed is. J equals, so pound motor number, J equals is returned to the pre-jog position command. Jog to position commands, pound motor number J equals constant or J equals star. J equals constant will let me jog to a certain number of counts. So I could say J equals 10,000. That will jog me 10,000 counts. If I was to say pound 5, J equals star, that would cause motor 5 to jog to a position that's specified by motor sub X prog jog pause element. So I would put the value of 10,000 in there and then issue the J equals star command, and that would cause me to jog to that position. Incremental jog commands, J colon constant and J colon star. So that will cause me to incrementally jog that number of counts. And the same thing with the prog jog pause element. If I was to do J colon star, it'll cause me to incrementally jog by the amount in that element. And then there are triggered jog commands. So I would specify any of the previously talked about jog commands, and then I would end it with a caret and a constant value. The constant can be 0. And so this would allow me to start a triggered move, and the final constant value could be 0, but it would also be the signed distance from the triggered position to the end position. Because on any triggered move, it's always going to go back to wherever it found the trigger. That's the whole point of a triggered move. So you can break into a jog move at any time with a new jog move or home command. You can issue these new commands as fast as the servo cycle. The latest commanded position, velocity, acceleration, and jerk values are used as the starting condition when blending into the new jog move. It uses the present values of jog speed, jog TA, and jog TS, and can be different from those of the executing move, the move that was already previously executing. You can break into an open loop move. So the motor's in open loop, and you start the jog command, whether it's enabled or disabled. It uses whatever the actual position and velocity of the motor it is as starting condition values for blending into the new jog move. PMAC, Power PMAC's homing feature. So there's basically two methods of establishing the motor's position reference. We can do a home search move. This means we can use an incremental sensor on the motor, and we use position capture to find the home position. Or we could use an absolute position read of an absolute position device. A little bit more expensive feedback device. But it does give us a number of options in setting up commutation, finding our position. Basically, the motor sub x.home complete status bit indicates what the position reference status is, if we have been homed or if we have not been homed. And it's used in both position methods. So it's set to 0 on power up reset because we haven't homed. It's set to 0 at the start of any home search move. And it's set to 1 when the specified trigger is found. So it actually goes true before the post-trigger move completes. So moving back to the home position, there's still the little bit amount of time it takes to get back to the position that it found when it found the trigger. And then it's set to 1 when the specified absolute position sensor is read. There's a number of ways to read absolute position sensors. So in doing a home search move, motor sub X home velocity, that's assigned. It's assigned floating point value specifying the motor units per milliseconds. So it specifies the direction and the velocity for doing a home move. It will use the currently set values for the jog TA and jog TS for that motor. There's also an optional home offset. So once it finds the trigger and what the home position would be, it would move to the offset, and that's also a signed distance from the trigger. Same thing as in one of the triggered jog moves where you have the the caret symbol and then the value after the caret symbol. So this provides that same functionality as the triggered jog moves. And then they're initiated with the online HM or program home command for the motor. Causes the search move to start. I think we might have a couple examples here in the next slide. Let's see. So we have a homing search profile. Here's the motor accelerates up to speed. Finds the home switch. At this point, it sets the home complete to 0. Now it has to make a controlled move to go back to the found triggered position, to what it captured in the capture register. So basically, we talked about the setting up for position captures, the same for a home move. So there's the PCAP flag. Capture control specifies how we're going to get it. Capture flag select tells us what's going to be the major flag that we're using. Is it going to be home flag, over travel limit flags, or the user flag? And then capture mode sets the trigger and type of capture. So a 0 does a true hardware capture from the PCAP pause register. This is a part of the gate that tells what the most recently captured position was. If we want to use a real hardware input trigger, but we want to do a software capture, we set it to 1. If we set it to 3, it will use the warning following error limit value for the capture. And then if we set it to 3, it will use the input trigger, but the timer assisted software capture that we can get from the gate 3. Remember, we have those timer A's and timer B registers that gives us some of these capture features. That gives us some of these extra, timer features. Then motor sub X PCAP pause specifies the address of the actual hardware captured counter. Normally we're going to look at the home capped A register, which is part of the, each gate has its own hardware for a special hardware register for captured position values. So we can see here, we start a home move in progress. Home complete starts at 0. Home move in progress bit will go to 1. It's in a triggered move, so it will set the triggered move bit to 1. And desired velocity 0 will no longer be true, so it will be set to 0. When the trigger is found, it will set the home complete bit to true, and the home in progress will go false, and the triggered move will go false because now it's making the post-triggered move to get back to that 0 position. At which time, the desired velocity 0 will now become true, and in position will also become true as long as we're within the fatal following error in position band. So processing the hardware captured position, it's in units of the ASIC register, so depending on what kind of feedback device we have, we may have to do a little processing on it. So we can take there are structure element names that let us tell capture position right shift specifies how many bits of low bits to shift out, and then capture pause shift left tells us how many bits to shift left after the right shift to match the servo scaling to the servo position, to match the result of the ASIC scaling, to the servo position. So again, remember, if we have P and ENC status set and the motor sub X ENC type, these are always set properly for us for the type of hardware that we're currently connected to. So here's an example. Digital quadrature encoder on the gate 1, on the PMAC 2 gate 1. So there's 24 bits of captured data because the gate 1 is a 24-bit device. And so we need to shift down 8 bits. So cap pause shift right is set to 8. Cap pause shift left is set to 9 so we can match the resolution with the servo data. And then there's this other one called cap pause round is set to 1 so that the half count bit is set to 1. And this is because on the gate 2 the servo is treating that edge as a half count. So for the turbo PMAC guys, you power up your PMAC and you always see that half a count on there. That is what is going on. That is what's causing that half a count. Now again, the automatic feature of the firmware will automatically set these up to the correct values for you after it goes out and looks and sees what hardware you're connected to. So if we were connected to a gate 3, it would set them up for the gate, the typical gate 3 settings. So the hardware position capture latches the position counter value at the instant of the trigger. We can also do a timer-assisted software position capture. I'll save this for a little bit later on in the class. I kind of want to get through the rest of these before we hit the 5 o'clock time limit. But basically, this allows us to almost get the accuracy of a hardware counter for feedback that's not using the actual counter register in the IC, like serial or parallel encoders, resolvers, an ADC that we're reading for our feedback device. And basically what it does is it's timing the time between since the last start of the servo cycle to the event of the trigger. So we can see there's the start of the servo cycle. There's the time to the trigger. We know what that servo period was. We can make a calculation to give us that very close approximation to where we were. Let's talk about absolute power on position. Motor sub x.pabs pause. This is the pointer to the absolute position feedback device. We can have absolute position sensors of many types. And this will keep us from having to do a power on homing search move. This can be a very big deal. For example, in a vertical axis, you might not want to have to do a homing search move. You'd rather know exactly where you are right away. So you also don't have to do a commutation search. And so you can immediately tell the motor where to start commutating, go into closed loop, and you also know exactly what position you're at. So we find that with the absolute position feedback address, motor sub x.pabs pause. If it's 0, then it disables that. By default, all of the absolute position values are set to 0 by default. There's motor sub x abs pause format. That tells us how we're going to use the data at that address. Motor sub x abs pause scale factor, how we're going to scale that data, any home offset to the motor's 0 position. And then there's motor sub x power on mode. Bit 2 will tell it to use the absolute position on power up. Or you can set it to 0 and then you would tell it to get the absolute power position with the HMZ command or the home Z command in a motion program. So those are the commands that would tell it to do an absolute read. So PABS pause specifies the address of the first register used. Depending on the type of encoder that we're using, it could be a serial encoder. It might be an absolute serial encoder, an absolute BIS encoder, absolute SSI encoder. We could be reading parallel data from one of the PMAC 3 interfaces, so that would be a GPIO data register that we would be looking at. Or it could be analog data from one of the analog encoders, so ADC from an analog feedback device. Accessory 28A, 28E can give us analog feedback. So if we take a look at the format of this power on absolute ABS pause format, this determines how we're going to read and interpret the data that's at that address that we just pointed to in this previous slide. So this position is going to be read by this process. So it's a 32-bit register. It's got 4 sections, A, B, C, and D section. The D section specifies the starting bit in that 32-bit register. The C section specifies the total number of bits to use, up to 48 bits. The B section specifies how to use the subsequent register. So if it's looking at multiple registers, how we're going to use the subsequent registers. And then the A section specifies how we're going to interpret the numerical value. The default 0, it's just a pure unsigned binary. A value of 1 interprets it as a numerical signed binary. 2, it interprets it as an unsigned gray code. And 3, it interprets it as a signed gray code. So if we were to look at this typical example, we can see the DD is a value of 8, so it wants to start at bit 8. 1C, so that's a value of 28 bits, so starting at bit 8, going for 28 bits. And then 08, it's going to continue at bit 8 of the next address because it's a multi-addressed format. So if that value is between 0 and 1 or 31, we extend the starting bit into that bit of the next word. And then finally, but not least, 01, we're going to treat it as a signed binary value. Okay, let's see here. I think I'm going to be able to get to the end before the end of today. So we can start with motor setup first thing in the morning. Let's talk a little bit about the leader gantry follower setup. So the motor servo control for the gantry leader is set to 1, and the gantry follower servo control is set to 8, and then there's another structure name that will tell us that this motor should look at the value in that structure name for its leader motor. So the slave motor is put into this mode as the gantry follower, and then the slave's motor, command motor structure or element will be set to tell it what it's looking at for its leader motor. The leader motor is typically assigned to an axis, so it's following a trajectory. And the follower motor is given the null definition in the same coordinate system because it's not going to be following a trajectory. You don't have to do that, but you typically want it in the same coordinate system so that it gets the same kind of fault handling as the leader motor in the coordinate system. So the whole point of doing that is to make sure that it gets assigned to the coordinate system. So this is much better than the old master-slave method of doing a gantry axis. And it's a lot more convenient than setting up two motors in the same coordinate system with the same coordinate system with the same axis name, because your gantry only works during a motion program, doesn't work during a jog move. So with the multiple motor leader follower gantry setup, it also works with jog moves. And you can have multiple follower motors. There's built-in skew removal so that we can remove the skew. The gantry leader motor must have its own home trigger. The gantry follower motors may have their own home triggers, and then we can get power on skew by using the Motor Sub X gantry slew rate. Motor in position function. So this is a status bit that will tell us when the motor is in position. A motor is considered in position when it's in closed loop control with the desired velocity 0, the move timer is not active, and the magnitude of the following error is within the motor in position band, and that these conditions remain true for motor in position time plus 1 consecutive servo cycles. And we can find that in the Motor Sub X in position status bit. And then there's a coordinate system in position. So if all motors in the coordinate system have followed these rules, then the coordinate system in position bit will then become true. And then we can use that in a motion program, for example, to wait for motors to become in position in the coordinate system before we move on to the next step in the motion program. We have motor backlash elements for a motor. We have backlash size, which specifies the amount of backlash in motor units. We have a backlash slew rate that specifies how quickly we'll bring in the backlash on reversal. And then there's also a backlash hysteresis. We'll specify how much of a reversal we have to have before backlash kicks in, so that you don't sit there and if you're sitting on a point where there's a slight amount of position change, you won't sit there and buzz on a point, vibrate on a point with backlash enabled. We have a motor trajectory pre-filter, so we can enable the motor trajectory pre-filter, and we can set up all of its numerator and denominator terms to give us a filter transfer function. So by default, it's set to 0. If we make it greater than 0, it turns on the filter and then sets the filter period in servo cycles. I won't go into the details of the pre-trajectory, the motor pre-filter, but there is an automatic setup feature that we have in the IDE that will allow you to set this up. I think a little bit later on tomorrow, one of our servo guys will come down and talk about some of the more advanced servo features that we have and that we can use in the IDE. We've talked a little bit about the Power PMAC servo algorithms. We have both feedback and feed-forward terms. The output typically represents a torque or a force for the actuator, and the execution is tied to the servo clock frequency. There's a number of built-in servo algorithms that we can select for the motor for different levels of sophistication, and we're going to see that here in just a couple of slides. We can also write our own custom servo algorithm and select and enable that for each motor. So we could write an actual C program, a real-time program in C. So motor sub x dot control specifies the address, the starting address of the servo algorithm that we're going to be using. Normally we just give it the name of the servo algorithm that we want to use. sys.pid control specifies a very basic servo algorithm, so there's none of the advanced filters in the servo function, but it does run extremely fast, so it could be used for those kinds of motors that you want to run very fast. Our default servo control algorithm, sys.servo control. This specifies our standard servo algorithm, so it's the PID plus the polynomial filters plus the deadband algorithms. We have sys.pause control. This specifies the output position as just a position command. So it's not looking for any feedback. This is typically used with the EtherCAT, with what we call cyclic position control EtherCAT drives. Sys.adaptive control specifies the adaptive algorithm. Sys.gantry X control specifies the cross-coupled gantry algorithm. And then if you want your own user servo, you would specify user algo.servo control address sub I for the custom algorithm that we would set up in the C section. And we'll talk about this when we talk about the C group. We'll talk a little bit about the adaptive control and the gantry control when our servo expert comes down and talks to you about the advanced features of the IDE. That'll be probably a little bit later on tomorrow. So here's a basic view of the basic PID control. Doesn't have any of the advanced features that we talked about. So on the basic PID, we have servo.kp, proportional gain, servo.ki, which is the integral gain, motor sub x.max DAC, which limits the output of the PI. And we have the velocity feed forward. Velocity feed forward in the velocity loop, or the velocity feed forward in the inner loop. And then we also have the velocity feed forward in the inner loop, but subtracted from the integrator. And this can be, I'll let our servo expert really describe the usages of these terms, but this can help in changing when you have dual feedback. We can use KVFB when we want it in the position loop, and the VIFB when we want the integrator in the velocity loop. So basically what we see there is if it's in the position loop, there's better tracking control, but if it's in the velocity loop, there's better disturbance rejection. But again, we'll talk about this a little bit later on tomorrow when we get into some of the more advanced features of the servo. Some of the important nonlinear terms that we have in the PID loop. The max position error. So this determines what this gives a clamp on the following error. Input to the position loop. Servo.max int. This gives a clamp on the integrated position error to the servo output. Motor sub x.max DAC. This is a clamp on the servo output magnitude. So this is your maximum, the maximum value, let's say in a plus or minus 10 volt system, the maximum output you would have on the DAC. There is also directly from the servo loop a DAC bias value that will act at the output of the PID loop. This is separate from the phase bias terms, which is different in turbo PMAC, which had its own terms for the primary and the secondary DAC output for a channel. And then there's motor sub x.comp DAC, which is, this is added to the output of the PID before the max DAC limit. This is the output either coming from a torque, this is the output from the torque compensation table, but you can also write to this yourself directly. Power PMAC also has input deadband compensation so that you can algorithmically create a deadband to compensate for an actual physical deadband in the system. So it modifies the following error value before the gain computations, and it can bring the gain down. If you want a true deadband, then basically setting motor.servo kbrake equals to 0 gives you a true deadband. If you set it greater than 1, then it can compensate for a physical deadband that could overcome friction from that point. And it does not affect the velocity loop. It's only in the position loop. We'll talk more about the adaptive servo control tomorrow. And the cross-coupled gantry, we'll talk about that tomorrow. You can execute the servo at the phase rate. So you can enable this for each motor by setting motor sub x.phase control bit 3 to a value of 1, to 1, which should be a value of 8. And then this will, for your very high bandwidth axes, this will allow them to close the servo loop at the phase rate. Power PMAC has the typical pulse and direction output mode. So you would have a pulse and direction drive, and then you would just be outputting a stepper drive, and you would be outputting pulse and direction. So on the PMAC 2 ASIC, a gate 1, there's an output mode bit that we would set up. We would set the encoder controlled for 8 to use the internal pulse and direction outputs. On a PMAC 3 style gate, there's a couple of ways that we can do that. The most typical way is to use timer mode 3 so that we're freeing up the encoder counter for use is either another encoder to be used by somebody else or as a check encoder for the stepper mode. And then the encoder conversion table processing is going to look for the single register value that comes out of the timer mode. And then some typical gains that we would use to give us approximately a 25 hertz bandwidth. KP would be set to 40. Velocity feed forward set to 0. Derivative gain set to 0, and velocity feed forward set to 40. Power PMAC can cascade servo loops, so you could have one servo loop fed into another servo loop. In this example here, we can see we have this auxiliary sensor. It could be a force sensor. So we have a position loop that we're closing a force loop around. A little bit later on in class, when we get into advanced topics, we can come back and talk about some of the details of setting up a cascaded servo loop. Let's talk about motor commutation, and this will close out the day for us. So when you have a typical three-phase motor, the drive can do the commutation on motor, or power PMAC. PMAC can do the commutation on the motor for you. So basically what's going on in commutation, it's switching the direction of the current phases in the motor to maintain the amount of torque you want and the desired direction of motor rotation. Brush motors are commutated mechanically inside the motor, so there's brushes in there that are switching back and forth between the phases or the windings inside the a DC motor. And brushless motors are commutated electronically, and this is what we're going to talk about in how Power PMAC does this. So why would we want to commutate a motor in Power PMAC? If the drive is doing the commutation, it's going to need a position feedback device so it knows where it is in the commutation cycle so it can do the commutation. So now you don't need a position feedback device going to the drive. The drives become more universal, less expensive. They're a simpler drive. It's easier to set up a torque mode drive. And Power PMAC can provide a very high quality sinusoidal commutation. Power PMAC can use only an incremental encoder to do its commutation. So Power PMAC can do a phase search move to determine where the rotor angle is in the current commutation cycle. Or you can use a low resolution sensor like Hall effect sensors to approximate where you are in the commutation cycle, and then do a home move. At the home move position, you're going to know you would have previously figured out what the exact offset to the commutation cycle is at that home position. Or you can use an absolute power on position feedback device to tell you exactly where you are in the commutation cycle. Power PMAC can also commutate AC induction motors and use those as positioning servo devices. So one of the nice things about commutation being done inside of PMAC, commutation in the servo loop being done inside of PMAC, now when you have a loss of feedback, you lose your encoder, there's not a runaway, there's just a loss of torque. So it just kind of locks into a phase. So it is, again, a much safer condition. If you're just sending out a plus or minus 10 volt signal and the drive is doing the commutation and you lose your feedback, the torque output's going to continue in whatever direction that it was, not seeing any following error, and that basically ends up being a runaway condition. So basic motor commutation setup elements: motor sub X dot phase control. This enables the commutation routines in PMAC. Bit 0 is set to 1. This enables pack mode. Bit 2, value of 4, is enabled. It enables unpack mode. You can't have them both turned on at the same time. It can only be one or the other. PMAC 2 style servo ICs can only use unpack mode. PMAC 3 style servo ICs can use packed or unpacked. So then it kind of depends on the amplifier features that you have, if whether packed or unpacked mode is going to interfere. So, for example, these Geo drives, even though they will work in packed mode, you lose some of the features on the ADC for reading back the fault numbers. So you see this, the display that's blinking here. I can read these values back over one of the ADC registers. Anytime the drive goes into a fault, I can read the fault values back. I can also read the status of the motor thermal elements on that drive. But if I put it into pack mode, now the ADCs are being used differently, and I no longer can access those features of the drive. Even though it'll still work, it'll still function. Motor sub x.phase enc. So this is going to point to whatever our feedback device is that's going to give us our commutation feedback, our commutation encoder. Almost always it uses the hardware register of the feedback device. Doesn't look at the encoder conversion table, but it uses the hardware register. So for the typical gate N, it's going to use the phase capture register. If it's a serial encoder data A register. If it's a resolver, it's going to look at the A10A register. Because in one revolution, both a sinusoidal encoder, a resolver in one revolution is an absolute position. Another commonly used method is some sinusoidal encoders actually have a third channel that's a single sinusoid per revolution, or they just provide a 1 sine per revolution output as the absolute position in one revolution of the feedback device. That's also common now. A motor sub X phase position scale factor. This is the pre-multiplication factor for that position value. So for a typical quadrature encoder, it's 1 over 256 of a count. Always uses the whole 32-bit register, even if the data is only left justified so many lesser counts of the 32 bits. We can process the source data before scaling with phase encoder right shift and phase encoder left shift. And this would be the typical calculation that you would do to determine the phase position scale factor. So 2048 units of the commutation cycle, and then n number of least significant bits in the commutation cycle. That ratio would be the typical phase position scale factor. So if you want to put that as an equation in your downloadable code to Power PMAC, I would always recommend letting Power PMAC do the math for you. You will get all of the internal 64-bit floating point capability of Power PMAC, as opposed to you calculating it and then putting it in as a floating point constant, literal constant in your code. Let Power PMAC do the math for you. Power PMAC can do sine wave output commutation. So Power PMAC can two types of commutation is the sine wave commutation and the direct PWM. So in the sine wave commutation, Power PMAC is basically computing the phase currents, but does not close the current loop. So it's outputting torque commands to the drive. The drive is doing the current loop. So controlling and making sure that the currents in the motors are correct for the amount of torque command that you've sent to the drive. So a typical sine wave output block diagram shows here's the direct current command that we have, the magnetization current, and then our torque command going into the DQ to ABC converter, and we just output 2 DAC, sinusoidal DAC signals, current loop being handled inside of the amplifier. So basically, since there is no digital current loop, PADC is set to 0. We will have a phase offset depending on whether it's a 3-phase motor or a 2-phase motor. So it's plus or minus 683 or plus or minus 512 for a 2-phase or a DC motor. We're going to point to Power PMAC's internal volt sine table for sinusoidal commutation. Sys.sine table 0. dot A, because we have to tell it an address. It's got a P there. And the PWM scale factor, plus or minus 32,677 for the full range of outputs. So in this case, changing the sign would reverse the direction sense of the motor in sinusoidal commutation, so you wouldn't have to swap reversing the motor direction sense for a particular command output can all be done in software when doing sinusoidal commutation. And then if we have any biases on the outputs, we have an IA bias and an IB bias. So that's the phase A output offset and the phase B output offset. Now with direct PWM command of motors in Power PMAC, now Power PMAC is going to actually not only compute the phase currents, but it's going to read the actual phase currents back and then close the current loop digitally inside of Power PMAC. So the command phase voltage outputs, these typically, and these are in most cases for our products, PWM outputs, and then these PWM signals are used to directly turn on the power transistors on and off. So there's the PWM A, B, and C. There's tops and bottoms, and this turns on the transistors directly in our drive product. So this is the way that we've designed it so that Power PMAC is doing all the calculations, and the drive end is just a simple power block amplifier. Then there's current sensors in the amplifier to measure the phases and digitize them back into ADCs so that Power PMAC can look at the current feedback and then determine what it needs to do to close the current loop. So here now that we see PMAC, and this little box here basically represents this thing called a Park-Clark transform. And so what we do is we have the torque command coming out. We have our current loop gains, closing the current loop, sending this to the Park-Clark transform. We're measuring the current values coming back from the motor into ADCs, and we're doing an inverse transformation of this transform on them to send back to close the current loop, and then the commands that then send the torque commands out that are turned into the PWM values that then spin the motor, controlling the PWM, and these are the current feedback devices, and then there's transistors somewhere in this section that these PWM signals are controlling. So for typical direct PWM output in a motor, again, we have the motor PADC. So this specifies the current feedback address. It's greater than 0 now. We've set it to the address of the current feedback devices. So a DSP1 gate, a gate 1, ADC 0. The gate 3, it's ADC amp 0, because remember, the gate 3 has separate ADC registers for the amplifiers and for the analog encoders, or just analog inputs in general. There's an ADC mask on the 32-bit word that tells us what bits to read for the ADC feedback. Almost always it's a 12-bit current feedback device, so the upper 12 bits will be turned on the ADC mask. And then there's a phase offset, which basically is the same, plus or minus 683 for a 3-phase motor, or plus and minus 512 for a 2-phase motor. And then the address of the PWM outlook table and the address of the current input lookup table. So that's P volt sign table and P sign table, motor sub X P volt sign table and sign table. And both of these will look at our standard sign table for both of these transformations. You can also create your own sign table in user shared memory. So the digital loop, current loop block diagram some of the direct current loop setup elements besides to continue with the direct current loop setup elements. So in closing the current loop, we have a forward proportional gain, we have a backwards path proportional gain, and we have an integral gain term, and then a cross-coupled gain term. This is multiplied by the velocity so that we can correct for inductive lag at higher speeds. We also have the IA and IB bias. This would be the bias on the current outputs, and then the PWM scale factor. Now, having seen all of these structure names and structure elements, there is a lot of automatic setup that we have in the IDE to set this up for you. So rarely will you ever have to go through and set any of these up by hands. In my case, that would be a lot of work to do. And I wouldn't want to have to do that. So we will almost always, in fact, tomorrow when we get started on motor setup, you'll see just how easy this is to set these up with our IDE and some of the automatic features of the IDE, including the current loop tuning. I already talked a little bit about the PWM signal generation. Basically, there's an up-down counter, and it's being looked at between these two values, and that cuts off the portion of the up-down counter, then ends up generating the PWM signal. And then at the beginning, at the first part of each PWM signal, there's a deadband time, so that you don't have two transistors being turned on that would directly short out your bus plus and your bus minus. Now, in all of our PMAC 3 amplifier products, we also have internal software that the amplifier has, and it is also checking to make sure that there is never the situation where even if the dead times were incorrect or somebody got them backwards, it would still prevent any of the two transistors from turning on simultaneously, thereby directly shorting out the bus going to the motor or the bus going through the amplifier. Another setup technique that Power PMAC has is the ability to set up a synchronous there's synchronous motor phase referencing. So we have to have some kind of initial phase referencing. The $ command, depending on what we've set up for our phase referencing and our motor power on mode bits, will determine whether or not we have an absolute phase search for the motor, or we read an absolute position sensor for the motor to develop the rotor position. So basically, for the phase search method, there's a phase finding output amount. So phase finding DAC specifies the current magnitude to use in the phases for doing a power on phasing search, and then a phase finding time specifies the settling time for each step in trying to find a phase with a motion power on or a specified motion phase finding. There are two main types of doing the phase finding. There's the 4 guess. So it makes 4 guesses 90 degrees apart of the phase angle and tests the response at each step of this 4 guess. So this moves much smaller. It's very good for frictionless systems, but it could have issues if you have a lot of friction, or if you have issues with the feedback. So basically it's measuring the acceleration at each guess, and it's trying to use that to determine what the generated torque would be, to determine if it is in fact on a phase zero. There's also the absolute phase position read, where we would specify in PAB's phase pause a number greater than 0. So this is the absolute register it's going to look at for its absolute phase position. And then absolute phase position format specifies how we use this data. This works virtually the same as the absolute power on position. And then we can also have absolute phase position offset. And so we can see the absolute phase position format is the same as it is in absolute position read format. We can use Hall sensor to approximate the absolute phase position read. And I must have missed the stepper method. Oh, stepper motor phase search method. I must have walked right past that. There's the stepper motor phase position method, which actually steps through the different, each of the different commutation cycle positions in the motor, and then it locks on to a phase 0 and then sets the phase position register to 0. In fact, I did talk about this. I just didn't mention that this was the stepper motor phase position search method. There's a technique that we can use to do direct PWM control of a DC brush motor. Basically what we do is we set the phase position scale factor to 0, and that way we get an infinitely moving output in either direction. And then finally, but not least, is induction motor control. Power PMAC can control induction motors. Induction motors are less expensive motors. You can get them in very large sizes. They're very rugged. It's virtually impossible to demag an induction motor because there is no magnet in an induction motor. So basically, in the setup of an induction motor, there is the magnetization current that needs to be set for the induction motor. Then there's the slip time constant, the slip constant for the motor. So it's set to the ratio of the phase update period of the rotor to the electrical time constant. And then the phase control bit is set to 1. Bit 0 is set to 0. Bit 1 is set to 1. And this tells it to use the slip calculations that would be necessary in controlling an induction motor. We can also do direct microstepping with the direct PWM of stepper motors. Typically, you would take sinusoidal output and go to 2 analog drives, connect those each to the separate phases of the stepper motor. But in some of our built-in drives, for example, in the brick LV, we use the ABCD. We have the 4 phases per output that we can connect up on the amplifier side. So we can directly control the stepper motor. You can directly wire a stepper motor to our brick LV product line and our power brick LV product line.